two key functions that we see a lot in biocalculus are exponential growth and exponential decay. Exponential growth curve looks like this. And we can think about this as time, and this is the world population here. And this would be the initial population when we start measuring. Exponential decay can be describing a variety of different things. In this particular example, I want to look at the urea concentration in a patient as a function of time while the patient is undergoing dialysis. The dialysis is removing the urea, and so the model is that it goes down exponentially. In these examples and the ones to follow, I'm not putting down the exact equations for the curves, but I'm talking about how we can interpret the curves in terms of the biology. So these are ones that you're going to see a lot of in this course: exponential growth and exponential decay. So the exponential function either grows or decays. But what happens if a function first grows and then decays? So it starts off increasing and then it starts decreasing. An example is blood alcohol concentration versus time. If you have several drinks quickly, your blood alcohol concentration will rise, but eventually it will decline again as your body gets rid of the alcohol. And so if we plot blood alcohol concentration as a function of time, we see rapid growth followed by slow decay. There's another place where we see something very similar, and this is with fish populations. And so if we think about this year's fish population on the horizontal axis and next year's fish population on the vertical axis, it takes exactly a similar form. It goes up and then it comes down. And so this is kind of interesting. What it means is if this year's population is very high, then next year's population could be quite low. Versus if this year's population it has some kind of intermediate value, then next year's population could be quite high. This is called overcompensation. So it allows populations to crash if they're very high, because next year they'll be low. This phenomenon was discovered by someone called Ricker, and so sometimes this is called the Ricker stock recruitment curve. And it's fit to a lot of fish populations, and it does a very good job of explaining how fish populations can boom and bust.